Hello everybody. We will start to discuss sampling and we'll present the central limit theorem. So in the last session, we looked carefully at the normal distribution, and I hope you spent some time, or you will spend some time, to work through some of these examples, because we will be applying this knowledge throughout the rest of the course. It's very important that you take some time for that. For this session, our learning objectives are then to discuss the reasons for sampling in quality programs, to calculate the distribution of sample averages from a given sample size from normally distributed random variables, and to explain the importance of the central limit theorem. Now, a reminder from the first session. This is a few weeks ago now. We introduced the concepts of a population and a sample drawn from that population. So if we have a population where mu and sigma are the mean and the standard deviation respectively, we can then take a sample from that population, and from the data that we take, we can calculate the sample mean, called that x bar, and the sample standard deviation, called that s, from the sample. And so again, mu and sigma were the population parameters, and x bar and s were the sample statistics. Now, as we also saw in session 2, if we only have a sample, we're actually estimating the average and the sample standard deviation. Sample average is calculated then as the sum of all the observations in our sample divided by n. The sample standard deviation is the square root of the sum of the squared differences. There's the differences of every value from the average squared divided by n minus 1. And the assumption for this is that all of our random variables are independent and identically distributed. Now, in this section, we will take a look at how to apply our normal distribution when we perform sampling as part of quality control and improvement programs. And we will discuss sampling plans then in more detail in session 4. So in the context of quality improvement, we will be choosing parameters to measure. Parameters which help us to understand how our process is performing. And in our example from tabletops, we could perhaps measure how long our tabletops are in our production. And we decide to take a sample of our tabletops every day and measure the length of all the tabletops in that sample. And why would we do this? Why would we do this? We're interested in how long our average tabletop is. How is our production running? What is the mean and the standard deviation? What are our population parameters in our production, in our tabletop production? We also need to think that if we measured every single tabletop, that would be too time-consuming and too expensive. So we take samples also to reduce costs, to increase throughput. Or maybe we've got a new saw for our tabletop production. We want to test how well the saw is cutting tabletop lengths. We want to try to improve the process. Maybe we have a new machine or a new method we want to test. And then we need to know how our population parameters have changed. So then we can use sampling then to look for changes in our process, or also just look for drifts and variations in our process, unwanted or wanted. And sampling then is used to make a good decision how our process is running and where we should move and how to improve our process. So this is the important part. If we take a sample, we've talked about random variables, tabletop lengths, for example. But if we take a sample of tabletops and we take the average tabletop length, the average of our sample. The sample average itself is a random variable. So if we take, for example, 16 sample tabletops every day, and we calculate the average every day from that sample, those averages will not be the same. Each time a sample is taken, the statistic x bar, or our sample average, will be a random variable x bar. So if x bar is a random variable, it needs to have a distribution, a mean and a variance. That's what we're talking about now. So we have a theorem. If x is a random variable, which is normally distributed, with a mean mu and a standard deviation or variance of sigma squared, then if we take a sample of size n, 16, 4, the average of that sample, x bar sub n, is also normally distributed with a mean equal to the population mean. But the variance is equal to the population variance, sigma squared, divided by n, where n is the sample size. Now this result says that if samples of size n are taken repeatedly from a population that is normally distributed and the averages are computed from those samples, then the averages themselves are a random variable which are normally distributed with a mean equal to the mean of the parent population, and here a variance smaller than the population variance. This depends on the sample size. As n goes up, the variance of the sample averages goes down. Let's look at an example. So let's say we are producing bolts. So bolts, you have a nut and a bolt. Bad drawing here. The bolt looks a bit like this. You have a nut that you screw onto it, used for making tables. You are looking at the diameter of your bolts. And you know that your diameters in your production are normally distributed with a mean of 2 inches and a standard deviation of 0.15 inch. You know that. You've made these bolts for a long time. Now you take a sample of 9 bolts and you measure those diameters. What is the probability that the average diameter from the sample will be less than 2.1 inches? Let's start. We have x, our random variable, is going to be the diameter of the bolts. Bolt diameter. We know it's normally distributed with a mean equal to 2 inches and a standard deviation equal to 0.15 inches. So the variance is 0.15 squared. Now, we take a sample of n equals 9, sample of size 9 of our diameters, and we calculate the average of that sample. Well, we know from our previous theorem that the mean of the sample average will be the same as the population mean, and the standard deviation, the variance, will be the variance of our population divided by n, where n is the sample size. And if we calculate that out, I mean, the mean hasn't changed. It's still 2 inches. And the standard deviation then, instead of being 0.015 inch, it's 0.05 inch, which, as we know, should be smaller. So now the question, though, was, we've taken our samples, we've can calculate the sample average, what is the probability that the average diameter of the sample will be less than 2.1 inches? Now that we know how to do. We can use our knowledge of the normal distribution to solve this. Now let's write this out. We're interested in the probability that our sample average from a sample of size 9 is less than or equal to 2.1 inches. And what did we have to do? To get the probabilities, we had to do our transformation and change to the z parameters so we could use our tables. Z is less than or equal then to 2.1, which is what we're looking for, minus the mean over the standard deviation. But which standard deviation should we use? Because now we're looking at the sample average, so we need to put our sample standard deviation there. That's the only difference from what we did before. And when we do that, this is a nice simple problem. If you can do that math in your head, you get P of Z is less than or equal to 2. And you can look that up in your table. The probability is 97.72%. 97.72% that the averages will be less than 2.1 inches. So it's the same exercise that we did before. It's just in this case we have to be aware that we're dealing with sample averages. And as we come in the essential limit theorem, it's very, very useful for us when we are actually working with real parameters. This is what is the importance of the essential limit theorem.